Good afternoon. Welcome to another lecture in a series of lectures for Chemistry 401. One brief announcement, I guess two brief announcements actually. One is the electrochemistry homework is due on Wednesday at 12:30, so no later than that. I will have office hours after discussion today, and then tomorrow morning, and then of course Wednesday morning as well if you have any questions. Second announcement is that there is an extra credit today. It is the Introduction to Undergraduate Research. I will be giving that presentation. It will last from 5:15 to 6:15 in this room directly after my office hour. And you sign in, and then you write a one-page summary, and I will be talking about the undergraduate research that I do with students here at Sac City. Any questions before we get started? If not, then where were we? Well, we were talking about transition metal complexes, and we said that where we left off was we were talking about high spin and low spin complexes, and the competition between delta O for octahedral, which I figured out for the middle of class, versus P, the pairing energy, due to placing two electrons in the same orbital. In Chem 400, we called that electron-electron repulsion. And the idea being that as you go from the, specifically for octahedral, since this is the octahedral splitting, as you go from the lower to the upper, the whole point of this is that these d orbitals are at a higher energy. And therefore, to put an electron up here is higher energy. To pair electrons in the lower orbitals, there is the P, the pairing energy. That is an energy associated with pairing. And the question is, what electrons, they always go to the lowest energy place. And we can tell which is lower energy sometimes by where the electrons go. All right. So now we'll pick up on so are there any questions about that? If not, then we'll pick up over here. It says we have a complex ion. It is diamagnetic. Determine the electron configuration, and if delta O is larger or smaller than P. The first thing we'll note about this is that this is octahedral. There are 6 ligands. Ammonia is a monodentate ligand. And so 6 of them, 6 attachment points, octahedral. And the other way of saying that is that the coordination number is 6. And if that's true, and that is true, then you can look on your conversion equation sheet for the pattern of the splitting. And for octahedral, it is 3 of the d orbitals lower and 2 of them higher. Just like I drew it here. And again, I know it's been a little while. We don't have to know which d orbitals these are necessarily. We just have to know that there are 3 low and 2 high. Then I'm going to take a second and I'm going to come over here and I'm going to talk about the cobalt atom. And then what I'm really interested in is the cobalt ions electron configuration. This is my process. I can see that there's a 3+ charge here, that there are 6 neutral ammonia molecules that are the ligands. That means that this 3+ charge is all associated with cobalt. So that's where I get the cobalt 3+. And as we'll see, sometimes it's cobalt 3+, sometimes it's cobalt 2+, and you're always working out what that ion is. All right. Well, looking at cobalt's position on the periodic table and writing out the cobalt atom's electron configuration, 27 electrons. The first 18 of those electrons are the same as argon. 4s2, 3d7, because there are 1, 2, 3, 4, 5, 6, 7 spots into the D, 3d7. Then we're going to take the 4s electrons away first. Again, why I always do the cobalt atom first is because otherwise it's tempting to, let's just say, mess things up. I'm going to take the 2 electrons from 4s. I need a third electron since I have a 3 plus charge. That leaves me with just 3 d6. Now, I'm going to start, I have to put 6 electrons into these orbitals. I have, for 6 electrons, or anything between 4 and 7 of the d electrons, I will end up having a choice where the electrons will always go to the lowest energy position. The first 3 electrons, there's never an option because they always go in the lowest energy. Next one, though, could either go here or here. Down here would be what's called the low spin choice because they will start pairing. Up here is the high spin choice. Since the problem says that the substance is diamagnetic, I will put the next 3 electrons down. So the fact that it's diamagnetic means that the electrons must be paired. And that's what we call the low spin configuration. Questions about that? Let's see. I always like to go back and revisit my own questions. Determine the electron configuration. That's this right here. And if delta O is larger or smaller than P, delta O must be larger than P because it's a larger energy, so the electrons pair instead. Good. Delta O is larger than P. The electrons pair because there's a lower energy pairing energy, or the energy for pairing is lower than the energy for going up to the higher. All right, I think I've answered the whole question. If I don't hear any questions for me. Now, I talked a little bit about the color wheel last time. Now is where we're really going to get into it. You'll see a variety of versions of the color wheel with slightly different wavelengths for all these positions. These are the wavelengths that we're going to use. As it says, perception of color is, depends upon the perceiver to some extent. So I know, like I said last time, you don't have this in color. Go ahead and write what the colors are. Red, orange, yellow, blue, or sorry, green, blue, violet, and of course, anytime you break colors into just 6 colors, these are a very broad classification, but these are the 6 that we'll use. And I believe what I said last time for the lab is that if you absorb purple, so if a solution absorbs purple or violet, it appears yellow. Did I do that example or did I do a different example last time? Different one? Because it all works if, right, so did I do absorb blue, appears orange? Appears blue, absorbs orange. And so it goes all the way around. Whatever one it absorbs, it appears the other one. That's it. Okay? Good question. Is there a mechanism or is that by definition? For Chem 401, that's by definition. Okay? And what I can say about that is, okay, the absorption spectra of many things are very complex. But what we're, and actually, let's start by showing you something. Here we go. The absorption spectra are complex. I'm showing absorption spectra here for nickel with 6 water ligands. Here, it doesn't say it, but this is nickel with 6 ammonia ligands. And you can see there are multiple peaks in here, multiple peaks here as well. And what we did is we, in the lab, said let's focus on the visible region. And ignore that. And so when you did your lab write-ups, you should focus on the highest absorbance that's in this visible region. And I did get this question. As you go down to off the edge of the visible region, you can see some absorbances, and we are ignoring that as well. And what we are going to say is that this absorption, which is even a little complicated in and of itself, and this absorption are due to an electron going from the lower to the higher energy orbits. So this one here. And what you should have done for your lab, or what you should be doing for your lab write-up for the transition metals, is you're looking for the wavelength of that peak. When you have the wavelength of that peak, you can plug it into the equation that says E equals hc over lambda, to get the energy, and that energy is the crystal field splitting energy. I'll say more. But next thing I'll ask you to notice. My notes say that this peak, and it doesn't actually look like it. Let's say this one's at 690 nanometers. And this one's at 570 nanometers. The next one is that as the ligand changes, the absorption changes as well. And I guess the way I'm going to put that is, as ligand changes, wavelength of maximum absorption changes as well. Wavelength of maximum absorption changes. Now we've got a picture of that here. And in this picture, we've got 3 different complex ions. We've got 6 ligands for water, 6 ammonias and 3 ethylene diamines. What we're showing is that as you go from one to the next, the delta becomes larger, and the colors of the solutions change. And if everything is working out well, I'm going to call this green. And if it appears green, then it must be absorbing red. Although it's a pretty anemic green. I wouldn't call it any, like you can't call it blue, I might call it an aquamarine. And so that sort of depends on where we are in here. So round to the nearest color. I'm going to call this purple or bluish purple, but I'm just going to call it purple. Oh, I'm going to call it bluish purple actually. Hedging my bets here because I'm going to call this one and so absorbs green, absorbs bluish purple, absorbs purple. Wait a minute. Appears, appears, appears. Absorbs, absorbs, absorbs. You're working your way around. So bluish purple, let's call it absorbs oranges, yellow. And absorbs. So then we're getting to this idea that the ligand changes, you get different delta values, you can observe that with the colors. And that's what you did in lab. You actually changed from nickel with waters as ligands to nickel with ethylene diamines as ligands, and you should have seen that change in color and absorption. Any questions about this? Things that you need to know about this for your exam. If I give you two colored materials, you have to translate it into the absorption and say which one has a larger delta value. So you'll have the color wheel, you'll have this color wheel, in fact, to help you do that as well. Now we get to what's called the spectrochemical series of ligands. This is a list of ligands. You will be given this list as well. And what this means is that as you move from iodide all the way through to cyanide and carbon monoxide, the crystal field splitting gets larger and larger. So for carbon monoxide and cyanide, largest delta value, way down here, smallest delta. For example, as you move from water to ammonia to ethylene diamine, just like on the last slide, you should see a larger and larger delta. Now there are some trends. I think I will ask you about the trends on the homework, but I don't think I will necessarily ask you about trends on the exam. So you should know about them. But the trends go like this. As you go in this shape on the periodic table, you can move from I to bromine to sulfur, all the way down to carbon over here. So there is a trend. It's a pretty general trend, and I am not going to require you to know that. I hope that's okay. What else do I want to say about this? That's it? Oh yeah, and look at this. Sulfur is sort of in here. Yeah. I like clear trends. I'm not convinced this is one of those. But what I will ask you is, depending upon which ligands I give you, you're going to have to know, well, these two colors, you're going to have to know that ammonia is a stronger field ligand than water. now a comparison. In this comparison, we've got cobalt with 6 fluoride ligands versus cobalt with 6 cyanide ligands. And both of them have the cobalt 3 ion. We just worked with this, so I'm going to go straight to the ionic electron configuration. It's argon 3d6. And the term for fluoride is that fluoride has a weaker field. Or a weaker crystal field. And so I'm going to draw the spacing of these two sets of orbitals closer together. And there are no numbers on this, but when I draw it for cyanide, cyanide has amongst the largest of the delta values. I'm just going to draw it larger. And these are relative terms. And we wouldn't know this unless I told you that one was paramagnetic and the other was diamagnetic, but it turns out that this compound is what's called a high-spin complex. Delta octahedral is less than the pairing energy, so the electrons go into the higher energy orbitals before they pair. With cyanide ligands, and again, we wouldn't know this unless I told you, this is a low spin complex, unless I told you it was diamagnetic. But the delta O is greater than the pairing energy. So they pair. We have a paramagnetic complex. Next question, what can you tell me about a deep blue solution of copper with 4 ammonia ligands? It's a rhetorical question. I'll try and answer it now. First thing is that the coordination number is 4. We have 2 different geometries that a complex ion can take with coordination number 4. One of those is square planar, the other one is tetrahedral. We don't know which one it is yet. So we'll write it as a question, square planar or tetrahedral. One good pen around here. Wow. Square planar or tetrahedral, we don't know the answer yet. What we know so far about the choice between square planar and tetrahedral, and if you look back in your notes, is that nickel, where's nickel on the periodic table? Here it is, nickel over here. Nickel, palladium, and nickel and palladium for sure. They tend to be square planar. We don't have any idea about the rest. But let's figure this out. We'll do the electron configuration for the copper atom, then we'll do it for the copper 2+ ion. Copper atom is one of the exceptions, meaning that it will have the first 18 electrons of argon. That's no exception. But it'll actually be 4s1 3d10. And then when we take 2 electrons away, of course, we'll take one of the 4s electrons, the only one, and one of the 3ds. Now, if you look back in your notes, and we just take a second and look at the tetrahedral splitting, versus the square planar splitting, you'll see that for square planar there are 4 relatively low ones and then a very high one. And then when a complex ion tends, when it is square planar, it will leave this top orbital empty because the top orbital is very high energy. So the top orbital tends to be empty. In square planar complexes. Because it's extremely high energy, well, or it's relatively high energy. On the other hand, if you have 8 electrons, then the other 8 electrons are all relatively low in energy. That's why nickel and palladium tend to form square planar complexes. Yeah. 3d9. Are any of the d orbitals completely empty? They can't be, right? All of the d orbitals have to have at least 1 electron. None of the d orbitals are empty. With D9, that's the copper 2+ ion that we're looking at. With D9, all the d orbitals have at least 1 electron. Another way of saying is that none of the d orbitals are empty. And therefore, for this complex ion, we will guess that it has the tetrahedral geometry. On the subtitles, for when Google does the subtitles for the automatic subtitles, I wish it would say, squeak, 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 squeak when I maybe in our infinite spare time we'll write that in. Okay, so now we come back. We've guessed tetrahedral. 1, 2, 3, 4, 5, 6, 7, 8. For 9 electrons, it doesn't matter whether this whole concept of delta, the splitting energy versus the pairing energy, because whether you fill in all the electrons down below or you go all the way up, you're going to have the same electron configuration. Any questions about this? Marissa and then Kate? why do we guess it's going to be the tetrahedral? Well, two reasons. Sort of one is, as you go through examples, what you will see is that the only things that you will usually see as square planar are nickel 2+ and palladium 2+. Things that have 8 electrons. So by experience, we will see this. And then the logic behind that and the reason is that the 5th orbital is so high energy that to put an electron up here is such an energetic penalty that it just doesn't happen. So things that have 8 electrons can put them all in these 4 d orbitals and leave this one empty. And in the end, lower the energy of the electrons. Whereas tetrahedral, basically you have 5 electrons in the higher one of these, and it basically tends to be a little higher energy than this. And I showed the picture probably in last lecture of all the relative splitting energies when compared to each other. If you look back at that, I think you'll find that, first off, that this is so high energy that putting 1 electron up here will be clear that it's not going to happen. I don't know that. Good question. So how do they know that the orbital splitting is there? Good question. I'm glad you asked. See if I can come up with an answer. So if I had D8, and I had 1, 2, 3, 4, 5, 6, 7, 8, and then I had, and then I looked at, well, this is the ground energy state. What would be one of the next, if not the next highest energy state? It would be for 1 electron going up here. So you could put energy in of different wavelengths, see which energy is absorbed, and it's not quite as simple as like, oh, it's obviously which one it is, but you could work out what the wavelength absorbed was for that transition, and then work out what its energy is. Does that answer your question? I mean, that's the same thing we've been doing, or we did with the octahedrals in class next time. But it's of course more complicated for this one because this would probably be in the UV. And you'd have to use the UV. Okay, question? Sort of. Palladium typically, and actually platinum as well. Yeah. So if your question is, let's say on the exam you're given a platinum complex, and the question is it tetrahedral or is it square planar? And you're like, well, it's got 8 electrons, it could be either, right? And the answer is, you wouldn't be given that question, right? Or let's say this, like the way I like to think about it is you will always have enough information to figure it out. And for platinum, you wouldn't. You'd be like, well, it could be this or it could be that. I don't know which one. I guess I'd have to tell you whether it's diamagnetic or paramagnetic or more information. Marissa? So, let's see. I don't know if this is going to work, but let's try it. There we go. It should work. That's why we're going to try. So, we don't usually need this, but to try and answer your question, I'm going to put like, what we usually look at is just the splittings themselves. But if we look at square planar versus tetrahedral, and we say, what? Wow, I don't think I exaggerated it enough. I don't know. It's way high, right? So from this picture, we know we don't want to put anything in there. And if you look at there's a splitting, so as high as this one goes is as low as these go. Okay? And then you can put the 6 electrons down here, you actually get much lower energy. This one's a little higher. And then, of course, we don't want to put any down. Here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 5 of these electrons that are sort of above this average place. And so, what I'm trying to convince you, and I'm trying to convince myself too, is that the higher energy for these, at least if you're D8, it's going to favor this. Is that? Yeah.
I just couldn't tell that from this picture that the tetrahedral's lowest energy state was still higher. But in your drawing, it doesn't seem like.
Yes, no, I'm sorry. I'd have no grid lines, so. But yeah, so if we come back to this picture, hopefully that ends up. Anything else? So, and just while I'm here, let's just remember, so these splittings come about because the ligands, as they come in towards the central ion, the different d orbitals, the closer the d orbital is to the ligands, the higher energy is. So that's how these pictures come about. Okay. Well, there we go. Why is nickel Cl4 with 4 chloride ions tetrahedral, while cyanide is square planar? Both have the nickel 2 plus. With 3D. Now and before I draw, I actually am going to try and draw these as close as possible to actual energies. If you come back to your spectrochemical series, Cl- is a weak field ligand. I don't think I need a colon. And cyanide is a strong field. So let me see if I can draw this, and let me see if the energies can make sense. And I'm going to help myself by exaggerating things. Let's pretend that that is a weak field ligand for a chloride. I've got my tetrahedral. And then for my cyanide, for my square planar,
No.
that's not the board, is it? I used to be able to get away with that when I had chalk and I was writing on. I could write on the walls because I could just erase it.
It's like we only went the whole semester without really going up there.
That's why I got to start teaching in rooms that have the chalkboard walls. And multiple, right, multiple, those sliding ones.
Yep.
Like then I could write it and then push it up towards the ceiling. Be awesome. Okay, so I don't know, what I'm going to attempt to convince you is that putting electrons up here versus putting electrons in this configuration, that there's a difference in energy. I'm not even sure I'm convinced myself, but I'm going to do it anyway. With such a low penalty or a low delta value, I'm going to consider this a high spin complex. Although you get the same electron configuration either way. Let me see, 1, 2, 3, 4, 5, 6, 7, 8. And so, weak field ligands tend to favor tetrahedral, even for D8s. The larger the splitting, the harder it is to get up here. And the larger the splitting for the tetrahedral will favor these square fingers. Questions about that? Question, it's always going to be tetrahedral. What is? This one? So weak field ligands will favor tetrahedral. Strong field ligands will favor square field. A modern example. Is what's called the ferrocene ligands. It is actually 2 cyclopentadienyl groups. We don't have to worry about the name. All we have to worry about is that this will form basically a bidentate ligand. And next we're going to attempt to convince you is that we can figure out what the crystal field splitting pattern is. Based on how close the d orbitals are to the open orbitals of the ferrocene group. Based on how close the d orbitals of Fe, well, this is going to be Fe2 plus. To the left. Now, so these are flat surfaces, and I'm going to ask you to notice this d orbital. See how close it is to the ligands. This is going to be closest. This one's kind of in the middle, so it's not as close as this one. And this one is completely flat. This one is farthest. when the d orbital and the ligand are closest, that means it's highest energy. Highest energy d orbitals, when they're the farthest, it's the lowest energy. And this one's just Now I have to put my splitting on here somewhere. I guess I'm going to put it in this space over here. These are my farthest ones. I have one in the middle, and I have two highest. This is the crystal field splitting pattern for ferrocene. Okay. So how did I know it's 2, 1, 2? So these two are the lowest energy ones because the d orbitals are farthest from the ligands. So farthest, what does that mean? D orbitals are farthest from the ligands. And in fact, this picture looks like 1, 2, 3, and these orbitals are pretty far. Whereas this one looks like 1, 2, 3, and so this is closer to the top and the bottom. Closest. So I know it's a little complicated to see three-dimensional pictures drawn on a two-dimensional board. But those of you who are going to organic chemistry, that's what it's all about. And we've done a little bit of that last time in Chem 400. We're going to do a little bit more of it. Does that answer your question, sort of, Kate, or do you have more questions?
I just learned on the test that all I have to do like just the way you drew it out.
Good question. What are you going to do if this is on the test? Well, I will promise you one thing. If this type of problem shows up on your test, that I will give you very good pictures. Better than this. We'll see. That's all. Okay, so where were we? And I guess more than anything, like when I think about why I did this example, like why are we doing this? I wanted you to be able to do a different example of looking at shapes of orbitals in proximity to the actual ligands. And this is a more complicated ligand because this has unhybridized p orbitals here. And the other reason is ferrocene is actually used in a lot of different circumstances. So if you Google ferrocene, it's interesting. Now let's talk a little bit about isomers. And isomers of complex ions, many kinds. You'll notice if you look at the transition metals chapter in your book, that's chapter 25, there's a whole bunch of stuff on naming of complex ions, none of which we're doing. There's a whole bunch of material on isomers. Most of it we are not doing. But we are going to do a little bit, and we're going to focus in on this one and a little bit about it. And sort of one of the ideas, or one of the reasons we're doing this, is because a lot of biological molecules, it depends on whether they run into either, which isomer they run into, how they react. And we're going to start with the example of cisplatin versus transplatin. Cisplatin, it has anti-cancer activity. Transplatin does nothing. And so the fact that just based on isomers you're getting different reactivity with cancer, I think is really interesting. So we're going to do a little bit about this. Cisplatin, well, let's just do I was going to draw it first, but I'm just going to draw cis versus transplatin. Cis will be right here. They will both be square planar complexes. So they're both square planar. This is cis. Cisplatin is going to have the two chloride ions close to each other. Transplatin will have them across from each other. Now let's do the same thing for an octahedral complex. We know this is octahedral because we've got 4 ammonia, single monodentate ligands, 2 water monodentate ligands. In this particular case, since it's octahedral, there will be 6 positions. Do you think this is going to be cis or trans? This is going to be trans. Where do you think, so if I put one of the waters right here, it actually doesn't matter. You can put them on any of these locations. I'll put it right here. And I've created my cis. Cis isomers have the same ligand close to each other. Trans ligands have the ligands as well. Now, question, Hannah.
I forget if you mentioned this before, but if you write it like NH3, that typically correctly goes.
So if you were to write this as NH3,
Like writing it left to right, I guess.
yeah, I'm fine with it. I guess the only thing you'd have to know is if you get a question about ammonia, how does it bind? or how does it bond as a ligand, I would expect you to know much. Now, what can you be asked to do on an exam? You can be given a formula, and I can tell you that it's square planar, and I can ask you to draw cis or trans for it. And typically there will be 2 of one type of ligand and 2 of another. And then, basically I can ask you to do these types of examples. Before I draw some optical isomers, I'm going to tell you what optical isomers are. Optical isomers are non-superimposable mirror images. That rotate the plane of polarized light in different directions. That rotate the plane of polarized light in different directions. Optical isomers are also called enantiomers. Enantiomers, that's an E at the beginning of that. And chiral compounds. And the best way I can talk about chiral compounds, how many people have heard of chiral compounds before? Raise your chiral hands. So chiral compounds, they are compounds that have non-superimposable mirror images like your hands. Does anybody know what the word chiral means in Greek? It means hand, right? And the idea is your 2 hands are mirror images of each other, but they are not the same thing. That's what these molecules are like as well. And I'm going to show you one example of chiral compounds for transition metal complexes. And then we're going to come back to them and really talk more about them when we talk about organic chemistry for our last unit, because that's mostly where we care about them. I will say this though. All biological compounds are chiral on some level. And that's why the interest. That's why we're starting to talk about it now. The example I've got here has 2 ammonia, 2 water, and 2 chloride ligands. I'm going to move my little cursor over there. And what I'm going to draw is and this is my mirror. I'm going to draw 1 iron on this side for this complex. It's an iron 2+, it looks like. And I'll draw on the ligands in a minute. Go ahead and draw those parts up now. Do you remember in Chem 400, those of you who had Chem 400 with me, how much of a pain in the butt I was about drawing out and back wedges? Well, here they are again, and we're going to see a lot more of them. Some more wedges here. I'm going to pencil in my ligands now. I know, I'm sorry, I wrote right over that one. Go ahead too. And what I'm going to do is I'm going to draw the mirror images over here so the top and the bottom don't change. The water that's on this side becomes on the far side. The ammonias stay the same since they're both, so I have 1 and 2, I have 1 and 2. These are non-superimposable mirror images. I'm not too concerned about this part, other than what you have to know. Let's see, what do you have to know about this? So first of all, you have to know the definitions of optical isomers, that they're non-superimposable mirror images, that they rotate the plane of light in different directions, that they're also called enantiomers, and that they are chiral compounds. So I guess you have to know all of number 2. And then these are pictures of them. And I don't expect you to be able to draw. More about optical isomers. Well, L and D here stand for levorotary and dextrorotary. Terms that we don't necessarily have to know either, although you will talk a significant amount about them in organic chemistry. Let me see. I think it's dextro that means right and levo that means left. Does that sound correct? And this is a picture of light that has all polarizations passing through a polarizer which selects one polarization. And then this is the sample. And it rotates the plane of light a little bit. And so you can see that the plane of light has changed. Rotates plane of polarization, so it's going straight up and then it's going back a little bit. And then you can observe that with your eye. I spent years working with polarized light for my thesis work. If you want to know more about it, great, happy to talk to you about it. But I just want to give you a quick example of what it means to rotate the polarization. Question?
Yeah, so in the sample, would you have optical isomers?
Yeah, so you'd have one of these, right? And the thing that's not clear is which one is right and which one's left. You actually have to test them to see. But once, so, and what will happen is when you get to organic chemistry, you'll come up with patterns to figure out which ones are levo and which ones are dextro.
So you like have both of those things?
But in this, you'd have one of them.
Oh.
And since this one is rotating the plane of light, well, if I'm this person and I look at the light, it appears to go that way, which is to the right. And so this would be dextro.
Okay.
Question?
Under normal conditions, are enantiomers equally likely to form?
Good question. Under normal conditions, are the two enantiomers equally likely to form? Yes. But there's a huge, and this is, we should save this for the organic chemistry part, but there's a huge market now for making singly pure optical isomers because you can make one that's biologically active without making them. And we'll talk about that. But this is Does anybody remember what this is? Anybody have these in their house? Old fashioned. Have to update myself. Have to think about that. Some LEDs are polarized already, which is interesting. All right. Now we'll talk more about this as well, but I wanted to show you a more common example of optical isomers. And it's actually not the next chapter, it's 2 chapters from now, but it's coming. And our working definition of chiral compounds for organic chemistry is going to be any carbon with 4 different things attached to it. And we'll talk more about what things means, but in this simple instance, we have carbon, central atom with bromine, chlorine, fluorine, and iodine attached. So I'll start with my mirror images. And then I will put as mirror images the different atoms bonded to it. And the key is they're mirror images of each other. And again, this is why it's important to be able to draw these with their wedges. This bromine is coming out of the board at us, and it is still coming out of the board at us. And these are like hands. Wait for it. That is the end of this chapter. We are back on schedule, folks. We're going to have, 2 lectures on nuclear chemistry. Those will be on Wednesday and the following Monday. Do we have? Then we'll have 2 lectures on organic chemistry, and then we will be done. So I'm just going to wrap it up here today. And we'll cover nuclear chemistry next time for 2 lectures. Yeah, we're back on track.